Welcome. This is your video taking a deeper dive into Niels Bohr and the electron. We have a little bit of assist from a couple of other scientists, namely Planck, Einstein, and de Broglie. So where we last left off in class, we had the Rutherford example of a nuclear atom. So we had the nucleus positive and dense. He later discovered the proton. It takes about 20 more years to discover the neutron, but there's nothing really complicated there. Once we know it's there, that's it. That's all there is to explain. Electrons get a little bit trickier because they're really, really tiny. So you can't really hit them with things like Rutherford did because they would essentially be obliterated. Like they're not going to make anything bounce off. And they move around too fast in order to have anything like deflect off. So we know electrons exist. That was the easy particle to find, but the difficulty is trying to figure out where they are. So what we end up having is the problem of the electron. How do we decide where they are and how to classify anything that they do? So I don't know if you remember me talking about the cathode ray tube as essentially a parlor trick. Something that people played with and they looked at, and it was a curiosity, just like magnetism and other electrical things, but they couldn't really explain it and they didn't know what it was doing. So in 1890, Ramsay discovers the noble gases, helium, neon, argon, all the way down through xenon. And the interesting thing about the noble gases is really the only interesting thing is that if you fill a glass tube with a noble gas, and you run an electric current through it, it glows. And it glows a very specific color. And this was a fun parlor trick, but nobody could explain why they did that, and nobody thought anything of it until Niels Bohr comes along and he does something a little extra to that gas discharge tube. So I'm going to play this video from a Phet Simulation. And what you can see here is if we had a sample of a gas in here and we shine light at it. Remember, light consists of all the different colors, right? White light, all the different colors. So you can see that represented by all these tiny little photons. And photons was something that Planck and Einstein came up with. But if you shine these photons of light here, occasionally what you will get is you will get a particle that spits out. And if you shine light long enough and you get all these little particles of light spitting out, you get this little diagram that's shown over here, this spectroscope. And that spectroscope for neon was very, very specific. And what it showed is that you got a color that came out that had 4 distinct lines. And I misspoke, it's not neon, it's hydrogen that they used. But you get these 4 distinct lines of color. Now when you look at the tube, it doesn't have 4 lines. It has 1 line. It has 1 color because color tends to blend in your eye. But he used this thing called a spectroscope, and we'll actually use one in class. But what a spectroscope does is it separates the color based on its wavelength, so you can see distinctive lines. So if you run a spectroscope looking at this hydrogen tube, you get 4 distinct lines. And Niels Bohr was like, why? Why 4 lines? I see 1 color. Why am I getting 4 lines? It doesn't make any sense. So he had to take this interesting idea about these lines of color and these individual photons or quanta of light and try and figure out what was going on. So continue to play the simulation here. So I took a picture. And what you can see is that the previous models of an atom cannot explain what's going on. So if we start with Dalton's billiard ball model, you're not going to get any photons of light coming out because it's a solid sphere. So everything is just going to bounce off. So we already knew Dalton's model didn't make sense, but now we know even more. Thomson's plum pudding model, well, that electron, sure, it can move and bounce around, but it's only going to spit out 1 color of light, and it's not going to produce that pretty spectrum that you see with hydrogen. And then we have the problem with Rutherford's model, and if you can see in Rutherford's model, there's that one electron, but it's not tied to anything, which means that there's no reason that the electron should do anything other than suck into the nucleus and explode. And that's what Einstein said, or classical physics would say would happen. So there's a problem. There's a problem with everything. And so what we have here is a notion that has got to be beyond classical physics, and it's called quantum physics. And Planck really came up with this idea that energy is quantized, or comes in tiny little packets. And it's easy to imagine light in little packets. When you see this simulation, you can see all the tiny little packets. And Einstein did a couple of experiments, as described in your text, that verified this. So Niels Bohr decided he wanted to kind of take this idea and run with it. So in this simulation, what you see here is what Bohr came up with. We have energy levels. And he said, okay, so if I have an electron, it sits on an energy level and it gets hit with a very specific quanta or photon of light, well, that electron can move and it can go from one energy level only up to another energy level. So if you speed up the diagram, you can see the electron jumping around. So when that electron is in that very first energy level, we say it's in a ground state, the lowest energy state possible. But when it bounces up to a higher level, well, what we get is called an excited state. And that excited state is unstable, so it has to fall back down. And when it falls back down, it's going to release a very specific and distinct quantity of light. And that distinct quantity gives us a single line of color in the spectrum. And so Bohr could show that for hydrogen, he could come up with calculations that would back up what they were seeing in these individual spectrum of different colors of light for hydrogen. And several other people did even further mathematical beliefs and all this sorts of stuff. But basically, Bohr gives us the idea that electrons can be in one spot, but not another. So we often get to the idea that light is both a particle and a wave. And that's kind of weird to think about, but it kind of makes sense when you're doing this type of experiment. So Bohr was really thinking about particles, right? That the light was acting as a particle bouncing the electron around. De Broglie kind of did the same thing, but he was imagining that the light was acting as a wave. And so if the light's acting as a wave and it's interacting with the electron, then the electron can kind of act like a wave. And that's what you see here, more like the electron is like a big rubber band that can get stretched out to higher energy levels and snap back to smaller ones. But it's the same sort of thing that a string that's making a wave, it can only be a complete wave, a total up and a total down. And so that you have to have a full wavelength, and that's going to give you full distinct circles. And I'll talk about this a little bit more in class, but these two ideas together produced the same mathematical results, so they kind of support and back each other up. Okay, so mathematically, anything that we can come up with theoretically is going to be nice, but nobody's really going to believe you unless you can back it up with math. So we've got a couple of calculations, and we're not going to focus on these too much, but they're simple formulas, and you should be able to manipulate them pretty easily. So the first one was Planck's equation, and this is what came up with that notion of quantized energy. So in this equation, we have, get my pen on here, we have three variables, and all of these probably look new to you. So first we have E, which capital E, that is going to be energy. And energy, as always, is in joules, capital J. We have this H, and it's an italicized H, and that is known as Planck's constant. It's a constant, isn't that lovely? Which means it never changes. And it is typically given with those 4 significant digits. And do note that is 10 to the negative 34th joules times seconds. And then there's this weird little thing, And that weird little thing looks like a V. It's not a V. A regular V would be velocity. That's a physics term. That's not a V. It's a Greek letter nu, N-U. And you kind of write the thing like that if you're doing it by your hand. And that is frequency. And frequency, if you're talking about radio, frequency is given in hertz. But if we're talking about chemistry, we do it in inverse seconds, which is s to the -1, or you can write it in 1 over s. But remember, word processors don't like fractions, so you'll see s-1 given a lot. So that's what you'll often see there. Now, to use the equation, I mean, it's an easy equation to use, right? So this is the question from your reading guide. What energy of light with frequency is 7.5 times 10 to the 19th, notice that is a positive number there, s to the -1. So, switch to pen. All right, so we need to set up this thing. So what do we know? We're asking for the energy. That's what we're trying to find. We're given the frequency. So this is our given. But I only have one number, and I've got 3 variables, but don't forget, one of my variables is a constant, so that's very easy. So E equals H times V. That's it. Well, H is 6.626 times 10 to the -34th joules per second times my frequency, my nu. So that's 7.5 times 10 to the +19th, s to the -1. Okay, so I've got s to the -1, so that's an inverse, and I've got seconds here. So those cancel each other out. That leaves me with joules for my unit, which should make sense. Now I want you to do a little bit of mental math here and think. I've got 10 to the -34th and 10 to the +19. -34th, 19. So I'm going to have a negative exponent in scientific notation here. And that would be, do it in your calculator, 4.9695 times 10 to the -14. But I need 2 significant figures, which is going to cut me off here, round me up there, and that 4.9 becomes 5.0 times 10 to the -14th joules, and that would be my answer. That is how much energy is given off by that frequency of light. And that's a small number, which should make sense, because otherwise we would probably die with the amount of light that we get hit with on a constant basis. We don't want it to be that much energy. Okay, so the second equation you need to be familiar with is not in your book at all, and it equates wavelength and frequency. So variable-wise, again, we see our nu, all right, our frequency. We see c itself, which is another constant. This is the speed of light. And then we have this thing. It looks like an upside down Y. It is lambda, and it stands for wavelength. We love our Greek letters. And that's going to be wavelength in meters. So in my AP chemistry class, Mr. Powell taught me this equation with a really lame joke that I will now share with you. He used to say, hey, what's new? C over lambda. Yeah, it's really bad, but he's a great guy. Anyway, so to solve a problem with this, what is the frequency of light energy with a wavelength of 409 nanometers? So nanometers, meters, not the same thing. So you can either move your decimal, or you can say that 409 nanometers is 409 times 10 to the -9th meters. Now, is that correct scientific notation? No, it is not, but it is just fine for putting into a calculator. So I'm looking for frequency. That's my nu. My C is 3.00 times 10 to the 8th meters per second. My wavelength is 409 times 10 to the -9th meters. I've got meters and meters canceling out. +8, -9, but that's division, so those are going to add together. 3 significant figures all the way around, and I get 7.33 times 10 to the 14th inverse seconds.